linear transformations. Now, we are learning so far, we've been covering the material from linear algebra, and the last major topics that we have discussed, we talked about the basis, okay, specific basis that can represent a certain space, and also, and by the way, before I start, I just want to modify a little more. I hope to make this slightly better. Okay, this is better. Good. So far we have discussed about the basis, and after the basis we discussed about the coordinates. Okay. So the coordinates, they were the projection of a specific vector or of a specific solution or a specific representation, the projection on a different basis, and we call those coordinates. Now, assume for a moment that we have a basis B1, okay, and a basis B2. So there are two different bases. How are these defined? Now, if we are discussing about let's assume for a moment, three-dimensional space. In three-dimensional space, the standard basis, let's consider this one as B. Standard basis in three-dimensional space is the following. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. We are used to this one. It's like X, Y, Z. And we can perceive these like this. Okay? So these are the three vectors, and this is the standard basis. Now, we know that this is not the only basis that we can use. We can also formulate a basis that might look like this. 1 minus 1, 2. 3 minus 5, 7, 1, 1, 9. Okay? So here we have another basis where each column that is here would be corresponding to these columns X, Y, Z. So each of the columns here, this is how we can consider those, right? And now, similarly, we can have also another basis B2. So probably we don't need to write it down, but we know that we can produce an infinite number of possible bases which all can span the three-dimensional space successfully. Now, the idea is that we can have a vector x, and this vector x, it can have the coordinates of vector x according to B1. This is how we denote it. Okay? So this would be the projection of a specific vector on this basis. We can have also the projection of a vector x according to basis B2. So we can have several representations, which means that we can switch the bases continuously. Now, when we do the changes between these bases, we do this using linear transformations. And these linear transformations, for the future few sessions, we're going to denote them as LT, linear transformation, or just T, okay, like a transformation. And we're going to see that either LT or T, they both can be written as equivalent to a specific matrix. So we can denote this equivalent to a matrix A. Okay? And with these, as this is with the matrix A, and the general idea is that we often want to switch from one basis to another, and we're going to see very often this picture. Having a matrix A and also any vector x in the standard basis, we can denote this one as SB. We may want to transfer to another basis, which we can consider this one as B1, and here we can have also another basis B2. Okay, and this matrix A here, this can be represented as D2 here, which is any other matrix D, and here a matrix D1. And this vector here, this can be considered as vector x2, and here vector x1. Why are these different? We are sure that this should be different because a single vector, which is one point in space, it is going to be projected differently on x, y, z in orthogonal Cartesian coordinate system, and it is going to be differently projected in some other bases that could look like this. Okay? What we are going to learn today is that we can change from one basis to another using transformation matrices, or let's call them transformation matrices. Let this be P1 and let this be P2. Okay, and then we can also So what this means is, in fact, this means that this vector x is equal to matrix P1 times x1. Okay, this is what this means. So this vector, in this standard basis, it looks like this, or it has these coordinates. The relationship between this representation and this one is defined by this. Or, at the same time, we can say that x1 is equal to P1 inverse times x. Okay, this is another. I think once we accept this, this is very easy for us to perceive, because we know that we can move backwards with the P inverse, P1 inverse. Similarly, if we can go here with P2, this is the matrix P, we can also come backwards with P2 inverse and so on. So this is the big picture, which we're going to see a lot, and this is the best part that you can learn in linear algebra. And I want you to refresh your knowledge, and please try to follow carefully, because these concepts that we're going to cover are very important. Now, regarding the linear transformations, any linear transformation T is defined as a transformation from space V to space W for, and here we want to have the 0, it's an element of V. So we want these vector spaces to have the V, the 0 vector in those. And at the same time, the linear transformation T, if we apply this one on a vector, 0 vector, this should be equal to 0, and this should also be a member in the space W. Now, we have a theorem, and the theorem is formulated as
Professor,
yes.
the result of transforming T with 0 is 0 or 0 vector?
This is 0 vector. You mean this one?
Yes.
Yes, this is 0 vector. Because these vector spaces V and W, just to refresh the knowledge, so that we don't get lost completely. What could the V be? I mean, give me one example for V.
R squared.
R squared. What if I call it this way? Let's assume that this is x0, and this x0, it is 7 by 1, okay? And here in W, which is a space, we have a vector x1, which would be 6 by 1, okay? So normally, this would be, but you're right, you gave an example, R squared, it's good. But apparently we can generalize a little further, where this x can be a subset, x itself, and also the V, which is composed of a lot of combinations of x0. They are a subset of R7. And the other one is apparently this x1, from which we can move through a linear transformation T. This would be a subset of R6 and so on. But you're good in correcting me regarding this. It's a 0 vector, not a 0. Unless the W is a subset of R, okay? Then we could argue that we do not need to put the vector sign. Now, the theorem that we want to talk about is the following. Let's assume we have a linear transformation which leads from Rn to Rm, with n and n being generalized. And then let E1, E2, En be the standard basis. Let this be the standard basis of Rn. Okay? And let A, now this A is a matrix, be a matrix composed of columns equal to, let me pick another. So the columns should be equal to TE1 T E2 and T En. Okay, then we can say that the linear transformation Tx, this is equal to Ax. Okay, so this is all we can. So what we did here, in fact, we just we are reporting, or we are saying that any linear transformation, it is equivalent to describing it as a matrix. Okay, and now one question here is, what are these E1, E2, and En? These are the standard bases, which are going to look like this: E1, E2, E3. Okay, so the standard basis, if we have five-dimensional space, and we have standard bases, the unit vectors, they are going to look like this. Okay, and the other one, or the fifth one, is going to look like this. So this is what we call E1, E2, En. At least for this course, think of those as we roll. Now this picture is so essential. I don't want to erase this, but I need to use the board. Okay. So for now, just we can take a picture of this, and we're going to bring it up on the board very soon.
Professor, I have a question.
Yes.
Should the E vectors be linearly independent?
Should what?
Be linearly independent.
Yes, they
Yes,
should.
because they form a basis for Rn.
Did you listen to your friend? So if it is a basis, they should be linearly independent. You cannot have a basis where the vectors that you have written down are linearly dependent, but now I believe you agree with it, right? E de acord?
Yes.
Ok, mă stăm pe minută de ducă bușmeni și eu am So if it is a basis, there should be linearly independent, all of them. And how do we control the linearly dependence or independence of a basis? What can we do?
If they are linearly independent, then we can express one of these vectors as sum of the other vectors multiplied by some constant, some scalar.
We cannot.
Yes, we cannot.
Okay, that's good. But how can we check it? What is a relatively fast way to check that?
The determinant.
I believe that's right. So we can take the determinant of which is composed by the matrix and by n, because it has to be a square matrix. Then we check the determinant. Now let's see an example here. And the example, it states that we have a linear transformation which goes from r cubed to r cubed, and it is such that t times x, y, z, this is going to be equal to the sum of the three numbers, okay? So we just do the sum. The difference between the first two and the third value is the first number plus twice the second one minus 3 times the third one. So here we have a linear transformation. What we get here is that we have a vector which is 3 by 1, and here we have another vector 3 by 1. So, and it is clear because we pick up a triplet of numbers from r cubed to another r cubed, so it's fine. But now the question that we do ask here is the following: what is A? This is a big question, okay? So we look at the linear transformation, find A. How can we find A? We look at this definition here, which we have it on the board. How can we find it? We just try to identify what is the linear transformation E1, right? What is the linear transformation on E2? And what is the linear transformation on E3? So these three, they will be...
To find three vectors that span R3.
Yes, so we do this. We do 1, 0, 0. What is the linear transformation T on 1, 0, 0?
1, 1, 1.
That's true. So it is 1 plus 0 plus 0, 1 minus 0, 1 plus 2 times 0 minus 3 times 0, right? So we get here 1, 1, 1. So this is the first column of the matrix A. Then, if we want to apply here for, I don't, we can denote it like this. So on this matrix here, if we evaluate at 0, 1, 0, what do we get?
1 minus 1, 2.
1, 0.
Professor, I cannot stay there.
You're not alone. You're not alone. Okay. So this is 1 minus 1, 2. Then, if we want to evaluate this one for 0, 0, 1, what do we get here?
1, 0 minus 3.
1, 0, minus 3. So the question that we asked initially, what was the matrix which correctly represents the transformation from R3 to R3 given these values? We can say that this matrix A, this is equal to the T on E1, T on E2, and T on E3. And this is all equal to a matrix which is 3 by 3, 1, 1, 1, 1 minus 1, 2, and 1, 0, minus 3. So here we have a matrix which is 3 by 3. Okay, then let's see, for example.
Professor,
Yes.
what if we could write the transformation in vectorial form? Like 1 x times 1, 1, 1 plus epsilon times 1 minus 1, 2 plus z times 1, 0 minus 3. And the columns should be the columns of A, but replaced by 1, 1, 1 for x, epsilon, and z.
And where would you see this directly?
No, I'm saying we know that t times x, y, z equals to x plus epsilon plus z, and that vector we have there. So if we could write the vector in vectorial form x times 1, 1, 1 plus epsilon times 1, 0, 1 minus 1, 2 plus z times 1, 0 minus 3, then the columns of A would be the columns of this vector form we found, right?
That's true. Yes, that's true. We can do it. Yes. Yes, but sometimes applying them on vectors 1, 0, 0, which are the E1, E2, and E3, things can become a little more intuitive and more generalized. And with the example we're going to see now, could work in my favor in terms of what you said is perfect. It's you are saying factorize here x, so which means the following. You could write here t x, y, z. This is equal to x times 1, 1, 1 plus y times 1 minus 1, 2 plus z times 1, 0 minus 3. So if we write it like this, then you are saying that each of the columns that we see on the board, they are the constituents of matrix A. That's true. Yes, we can do that. Now, let's see a rotation of linear operation. So now, in fact, it looks like the matrix, so let me ask also this question. So here we have a matrix 3 by 3, right? This is the A we just came up with. Now, what happens to a vector that looks like this? 1, 0, 1. What would be the answer? So here, we just multiply this matrix A by this x.
2, 1 minus 2.
2, 1 minus 2. Is this correct? 1, 2, this is, no, yes, 1, that's true. 2, 1 minus 2, that's good. Now let me ask you this. What is the magnitude of this vector here?
Square root of 2.
Okay. What about the magnitude of this vector here?
1. No. 3.
3. 3. So this is 1.4, this is 3, right? Now, what happened here is that we have a matrix A, we're multiplying it with x0, and this is equal to x1, right? Vector. So what was 1, 0, 1? So let's think for a moment. This is x-axis, this is z, and the y-axis is pointing out of the board, right? X cross y, the right-hand rule, we can say x and y, we get this vector. So if x is 1 and z is 1, we have a vector, and y is 0, we have a vector which is right here on the board. Then we multiply with this matrix, this vector, which we can see here, and what we get 2, 1, so x is 2, y is 1, sorry, z is minus 2, okay? Z is minus 2, y is 1. So from here, we come this way, and with respect to the whiteboard, we move 1 unit out, okay? So we're going to have a vector, which is kind of be coming up like this. Would you agree with this? So what happened with this x0? With this x0, the first thing that happened, it rotated, okay? It rotated. The second thing that happened is that it expanded. It increased in size from 1.4 to 3. So it's like expanded twice. So this linear transformation, it could be represented as, we could first rotate the vector x0, okay? And then, after we rotate, but where do we rotate? We bring it from here to this vector here. And then we can apply another linear operator, which is elongation, something. We change the length, and this would be equal to x1. So, just think about this for a moment. So apparently, these matrices that we always use, that's what they are doing. They rotate the vectors, and they also change the length. Now let's assume a linear operation, which just does the operation counterclockwise by an angle theta. Okay? Then let's see what happens. So let's try to represent, the question is the same. We have a linear transformation, which will have a rotation counterclockwise by an angle theta. The same question we asked here, we are also asking it again. How can we do this?
For what spaces? R3 and R3?
R squared. Let's do R squared because it's easy for us to draw this. Okay. So how can we do it? A general form is always this. Okay, so we can do this. If we are in R squared, that means that we have to look for what is the transformation on E1, which is the transformation on what? On 1, 0. What is the transformation on E2, which is the transformation of 0, 1? So now, here we have the 1, which is this vector, and here we have the other vector, 1.
We already know the angle they form with the x and epsilon axis.
What do we know?
The angle they form with x-axis.
What is the angle?
For 0, 1 it is 0 degrees, and for 1, 0 it is 90 degrees counterclockwise.
But let's think about this one. Let's say that we rotate this one by an angle theta, okay? And what happens when we
denote the new vector by x epsilon, and we know that the dot product of 0, 1 with x epsilon divided by their product of magnitudes will give the cosine of the angle.
Yes. And what should we get then if we rotate this vector 1, 0? What do we get for x and what do we get for y?
We could also use a
Cosine
rotation
theta
matrix.
and cosine theta.
Yeah, cosine theta minus sine theta, cosine theta.
But so, say it slowly. What should I write here?
Cosine theta.
Yes. Okay. What about the y?
Sine theta.
Sine theta. That's good.
Minus sine theta and cosine theta. Then
for the other one, right?
Yes.
So let's rotate this one here. If we rotate this 1, 0, we get this projection onto the y-axis and this projection onto the x-axis. So here, the linear transformation on 0, 1, this is going to be equal to what? So initially, the projection onto x-axis, it was 0. Now, the projection onto x-axis is this vector, which is equal to what? You said it. It is minus sine theta. Because sine theta is this short side, which the Briner Spurter. The Briner Spurter structure. And it is sine theta, but is with minus because it is pointing along minus x direction, and this is cosine theta. Okay? That's good. So here we have a rotation, and the matrix which represents this rotation, we can write this one as a theta. This would be equal to cosine theta, sine theta, minus sine theta, cosine theta. So what is the determinant of this matrix?
1.
1.
The determinant here is equal to 1, and whenever the determinant is equal to 1, we call these matrices unimodular matrices. Okay? Unimodular matrix. These types of matrices, they have special properties. They are used a lot in numerical analysis and in mathematics. And the major reason is that because of specific properties that come up from the determinant, they can preserve certain properties, or they can preserve certain features. Now, what would this vector be equal to if the angle is pi over 4? Ce se cădește 205 grade. S-a de matrița?
Square root over 2.
1 over square root
of 2 over 2 minus. It's the same for the rest.
Okay. This is when the angle was theta is pi over 4, or this, now these are not equal, right? This is equivalent. You know that this is valued for this value. Okay, sorry about that. But what about if the angle is pi over 2?
Minus 1, 0, 0, minus 1. Minus 1, 0, 0, minus 1.
Where is minus 1 is here?
0.
0, minus 1.
Minus 1.
1, 0.
Is it true or no?
Yes.
Sine pi over 2, it looks like it's correct. So here we can construct rotational matrices. Now, let me also ask you the following. What is A minus theta? A minus theta, this is it.
It's cosine theta.
Or sine minus theta. Sine minus theta minus sine minus theta. And cosine minus theta, right?
It's the
The sign of
transpose.
cosine doesn't change, but of the sine it becomes minus. Okay. Plus sine theta and cosine theta.
This is correct. I hope you
So
all...
this matrix is the inverse of the first matrix,
Okay.
I think.
So,
The transpose.
Transpose.
is it also a transpose? Oh, you are good. That's really good. So now let me take this away. So if we multiply a theta by a minus theta, we are going to have, so here we have cosine theta minus sine theta. We have to multiply them like this. I imagine this row. Actually, I don't want to write everything from scratch, but this is cosine minus sine, sine, cosine times, we got here cosine minus sine, sine, cosine. Now, this was in fact A, okay? And you correctly said that this is also A transpose. But A transpose is in fact also equal to A inverse. And matrices whose transpose are also inverses, they have very important properties, especially when we try to change the basis of specific representations, specific solutions, specific vectors, and many more. But let's see now what we get if we multiply these. Well, we know that if we rotate something counterclockwise, and then, so from here, we rotate counterclockwise and then clockwise, we should get the identity matrix, but let's check what we get. So if we multiply the first row with the first column, what do we get?
Cosine squared theta minus sine squared theta.
Yes?
Then we
Professor, I
get
cannot see there.
sine cosine minus, we get 0.
Do you mind getting to the other row? Oh, okay, it's fine, thank you.
Say it again?
0.
Yeah. 0, 0, 1, right? So which is the identity matrix in fact? Okay, so these were linear transformations which were dealing only with the rotation. Okay, so if we have any vector which is, let's say, we can pick up vector 3, 2, or let's pick up this one. So A, when theta is equal to pi over 2 times x0, and here we can represent 0, 1 minus 1, 0, 0, 1 minus 1, 0, and we multiply with a vector 2, 1. What we get here is that we get minus 1, 2. And if we try to draw this 2, 1, it's 1, 2, 1, and then it's this vector, and then we get minus 1, 2. Okay, so this is x0, and this is A times x0. So what happened here is that we rotated the initial vector by an angle of pi over 2 without changing the magnitude. Okay. Now this angle can be any angle theta, it is generalized. So if you want to rotate any vector, this is all we need to determine. Now this was just a rotation linear transformation. Now we can have identity linear transformation, and identity linear transformations, the way that they are defined is that TV is equal to the same vector V, and the matrix representation, it should be the identity matrix. So we can even write this one as identity matrix times any vector V. We can have also zero identity. Zero identity would be in fact any t times v would be equal to the zero vector. Okay, so which means that the linear representation of this t, this could be equivalent to representing all of this times any vector x, and this would be equal to 0. What does this remind us?
We have to solve
Now-
the system to find matrix A.
Yes, we have to find
It reminds us of us finding the null space.
That is correct. Okay. So linear transformations, what happens is that we have a domain here. Okay. This is the domain where we get the values and we apply a linear transformation to go to the range. And so we can go this way using a matrix A. How do we do it? We pick up a vector here. The coordinates of this vector here, x, is an array of numbers. We pick this and we bring it this way. But now, and they all send us to this 0 point. But now, finding this x is, as you said, it's equivalent to determining what is the null space of A. Now, I did not draw this one correct. What is wrong with this figure? So, assuming that the null space is a plane, and I try to draw it here, what is wrong here?
The plane has higher dimensions than the vector.
No.
It needs to be straight.
Doesn't go through 0.
That's correct. It doesn't go through 0 because the null space should include the 0, right? So the null space we find it here, but the range of the matrix is here. So we have the null space, the range of. So do whatever you can. So this cannot be the null space of A, in fact, but it should pass through 0 somehow. I mean, it should be. Now you know this. Maybe I'm not going to draw it again, but as we're talking about the linear transformations, we have linear transformations which we can call them as identity transformations, which means that we're just multiplying the vector, or a linear transformation times a vector x0 is also equal to x0. Now, other linear transformations, we can consider a combination and composition of linear transformations, okay? So,
Can you move the camera to the left, please?
yes, I should. Yes, sorry.
Thank you.
You're welcome. Okay, so now with these linear transformations, we can also assume that we can have a combination or different compositions of linear transformations, and we can assume that if T is a linear transformation from V space to W space, and another linear transformation S can transform or can transform from W to U, then ST on V is a linear transformation from V to U, okay? So this would be equal to S times any vector W, and this is all will be equal to some vector in U. And SP, we can also denote this one as, with this, we can pass from V to U. So this is another linear transformation. And as we said before, it could be possible that any matrix A, it can be represented as a rotation, okay, times another operation which can have an effect on the length. So it can expand the vector, make it longer, or compressing the vector, making the vector shorter. So we could have either one of these, and in fact, let me think for a moment. So if we have here ST operating on a vector V, this would be equal to U. And now this T, this can be represented by matrix A, and S can be represented by matrix AS on V, and this would be equal to AS times S80 times V, and this would be equal to vector U. So here we see that a combination or a composition of few or several linear transformations, they can be represented as simply as matrix multiplication. Okay. So we can apply a few of these, and this is what we can get. Now, if you like, we can have a short break. And if you have any question, you can ask.